Thanks all for staying until this last talk for today. This one is about dichotomies for counting subgraphs, and it's a joint work with Daniel Marks. So in this talk, we'll be interested in counting subgraphs like these here. And essentially what we want to do is, for each graph, say whether the graph is easy or hard. And okay, I have to specify a bit what I mean about this. So first of all, the problem that we'll be studying in the entire remainder of this talk is you're given as input two graphs. One of them is a pattern graph on k vertices. The other graph is a so-called host graph on n vertices. And what you're interested in is the number of subgraphs of G that are isomorphic to H. And by subgraph here, I mean a subgraph that is not necessarily induced, although at the end of the talk, I'll hopefully also have some time to talk about induced subgraphs. But in any case, this is the problem that we're studying. And you can see that for each fixed graph, this problem is in polynomial time. So the question I mentioned at the very beginning of the talk is actually solved. And I should have told you earlier that this will be a very short talk, which is, of course, not true. Because the actual problem that we study is that we fix some class C, and we restrict our pattern to be chosen from that class. And this gives rise to this problem count sub C for a fixed class C, where the input is a pattern from your class, which is fixed, and you're given a host graph. And you just want to output this number of subgraphs of H and G. And then there are, of course, many classes that you can look at, like cliques, cycles, stars. And for each of these classes, we ask ourselves, which class makes the problem polynomial time solvable? Okay? So if we study this problem from a classical point of view, then, I mean, this answer here can be resolved by classifying the problems into polynomial time solvable or Sharpie hard under, let's say, Turing reductions. This is what you usually get in a classical setting. So let's try to apply this classical setting to the subgraph counting problem that I defined. So again, we have this problem for fixed classes, and the question we're asking is, well, again, which classes make the problem polynomial time solvable? But now we have this extra assumption that we can use that fp is not equal to Sharpie, because obviously we have to use some assumption. So cliques are Sharpie hard just because deciding cliques is NP hard and there is a parsimonious reduction. Counting cycles is Sharpie hard because you're counting Hamiltonian cycles. If you pick the pattern to have n vertices, then again, this is Sharpie hard. But for instance, stars, they are easy actually. So you get a polynomial time algorithm, which is actually even linear in the size of the host graph. So a star is a vertex that has a center vertex like this, and then k rays. And if you want to count the k stars in a graph G, then you can just do this by summing over all vertices in G. And for each vertex, compute this binomial coefficient, which is just the degree of V choose k. Because once you fix a mapping of the center vertex into your graph, this is just the number of ways you get to distribute the rays among the neighborhood of V. Okay, so it seems that assuming fp is not equal to Sharpie, for these classes we can get a good picture what is easy and what is hard. But unfortunately, the general situation is a bit worse. So there are classes for which we apparently don't get such a classification. So here is a class, this class C, which consists of graphs that are T cliques together with 2 to the T isolated vertices. So they're just padded cliques, so to say. It's maybe a weird class, but it exists, and we would still like to say what's going on there. So you can see that this class actually, if you want to solve the subgraph counting problem in this graph, you get a quasi-polynomial time algorithm. Just because, well, to count the HTs appearing in G, you can just count the the T cliques appearing in G, and just multiply by this number of ways to map the isolated vertices into the remainder of the graph. So altogether, you just need to count these T cliques and do this multiplication. So you end up with a running time of n to the T. But T is logarithmic in the size of the pattern, and the pattern is always bounded by the size of the host. So you really get this quasi-polynomial running time. But this is also the best running time we know of. So it doesn't seem that you can solve this problem in polynomial time. And one problem that we have here is that since it's quasi-polynomial time, we don't assume that it's Sharpie hard. So this seems to be a candidate for a problem that is Sharpie intermediate. And in fact, if you do a more clever construction than just picking 2 to the t isolated vertices, but doing something along the lines of Ladner's theorem, you can actually get truly Sharpe intermediate classes. So, okay, if this is the question that we want to ask, then we have a problem, namely Sharpe intermediate classes. We won't get a dichotomy. But, I mean, this kind of gives us a theoretical problem, but from a more practical point of view, there's another problem with this model, namely, we cannot do reasonable statements when the host graph is supposedly much larger than the pattern graph. So for each fixed pattern, you get a polynomial time algorithm. If the pattern grows very slowly, let's say like log n, you get these quasi-polynomial time algorithms again. So we don't really know what's going on there. And I would say that this is probably the most natural model where the subgraph counting can appear. Because usually you have situations where you have a small pattern which appears in a huge graph. Like, I don't know, you want to count cliques of size 6 in the Facebook graph. So then you can assume that n is huge, and, well, 6 is not particularly huge. So to get rid of these two problems, we actually don't study the problem under fp not equal to Sharpe, but we pick a different model to study it. And this model would be that of parameterized complexity. So in parameterized complexity, the situation that we have is that we're looking at parameterized counting problems. So such a problem is just given some input, output some number. But now we have this additional parameter, kappa of x. And the parameter in a problem like this is just a function that maps inputs to natural numbers. It's supposed to be computable. And the idea is that the parameter measures some notion of instance hardness that is more refined than just looking at the instance size. Okay? So there are a lot of examples for parameterized problems, also parameterized counting problems. But let's just use this definition to get a parameterized version of counting subgraphs. So we just take this subgraph problem for fixed classes again, count subgraphs from a class C, but now parameterized by the size of your pattern. So this would be one good example for a parameterized problem. Special cases of this problem would be counting k cliques on parameter k, counting k cycles on parameter k. So k cliques is supposed to mean cliques of size k. But there is also a problem which is not a subgraph counting problem, and that's given a graph and a number k, which is the parameter, output the number of k vertex covers in your graph G. So if you look at all these problems, then you can see that you can solve each of these problems in time n to the k plus some constant, because you can just brute force over all possible solutions. So this means that for each fixed k, you get a polynomial time algorithm. But the task in parameterized complexity is now to drag this k out of the exponent, so to say. So this leads to this notion of fixed parameter tractability. So a problem is fixed parameter tractable, or FPT, if you can solve it in time f of parameter on x times some polynomial in x, where f is any computable function, and in particular a function that may be super polynomial. So, well, one classical example would be, for instance, that this first problem of counting k vertex covers is actually FET. So you can solve it in time 2 to the k times n, meaning you get a linear time algorithm for each fixed k, which is, of course, better than getting just some polynomial time algorithm for each fixed k. Okay, but generally speaking, we would like to know what happens for these three problems as well. So can we get FPT algorithms for these problems as well? That's kind of a question that we will be trying to answer in the remainder of this talk. But to do this, we need some model of hardness for parameterized problems. And that's the part where we need some complexity theory for parameterized problems. So this leads to parameterized counting complexity, which was introduced by Flum and Grohe. So I should say that parameterized complexity was introduced by Downey and Fellows like 10 years before that, at least 10 years before that. But the counting versions of these problems were just defined later. So in parameterized counting complexity, again, the easy cases, which correspond to polynomial time from our classical setting, are FPT, and the hard cases are Sharpe W1 hard. So sharp W1 hard is the analogon of sharp P hardness. So a problem is sharp W1 hard if, and this is maybe a bit of a lazy definition, but I mean, you can define it that way, and it's better than taking some machine model, in my opinion, at least for the purposes of this talk. So one canonical or one heavily used definition of sharp W1 hardness is just that you can reduce counting k-cliques to your problem in question by a parameterized reduction. So what does that mean? It just means that you have an algorithm that solves the problem of counting k-cliques with an oracle for this counting problem sharp B. And the running time of this algorithm is supposed to be fpt in k. So it's computable function in k times polynomial in n. And the second restriction that you also need is that whenever this algorithm issues a query to your target problem sharp B, then the query will be bounded by some, the target parameter of your query will be bounded by some computable function of the source parameter.
I'm missing, what's the connection? We have k and kappa. What's the roles here?
Okay, so k is the parameter for counting k-cliques,
Yes.
and kappa would be the parameter of your target problem. So two parameterized problems can have different parameters. And you want to reduce counting k-cliques to counting b, and b has this parameter kappa, whereas k-cliques has the parameter k. So if you want to solve an instance of counting k-cliques, you want to do this by calling the oracle only on instances where this target parameter kappa is bounded by a function of k. That's just the thing. And you need to enforce this because otherwise you don't get this, which would be closure of FPT under FPT reductions. And that's, of course, something you need to do complexity theory. So in other words, just if we now were able to prove that sharp B is FPT, then we also get that counting k-cliques is FPT. And this is something that is believed to be very unlikely based on the evidence that the field gives us. So that's parameterized counting complexity. And if we apply this now to the problems we looked at before, then we essentially just defined counting k-cliques to be hard. But interestingly, you can also see that counting k cycles is also sharp W1 hard. So Flumengro showed a parameterized reduction from counting k-cliques to counting k cycles. And that's interesting because, it is known that deciding whether your graph contains a k cycle is actually fixed parameter tractable by a technique called color coding. So you can solve it in exponential time in k times polynomial in n. So in a way, this is like comparable to the sharp hardness result for counting perfect matchings. Here we have a problem whose counting version is hard, but its decision version is, NP hard, but FPT. Okay, and of course, for the general subgraph problem, this will have to depend on the class C. And let's just gather what we learned so far. So the new assumption that we can use now is assuming that FPT is not equal to sharp W1. We're going to ask when is the subgraph counting problem from the class C fixed parameter tractable. Then cliques are hard, cycles are hard, and k-stars, well, they stay polynomial time. And what about this pathological class that we studied earlier and which was some kind of counterexample in the classical case? So what about these graphs HT that are T cliques with 2 to the T isolated vertices? They're also sharp W1 hard. Why? Because there is, the algorithm I mentioned before that got us quasi-polynomial time is actually an FPT reduction if you just do it the other way around. So if you want to count K cliques with a reduction by reduction to counting HK, just count HK in G and divide this binomial coefficient out, and you get the number of K cliques, assuming that n is large enough, but it's okay to assume that. And the running time of this is just the time you need to write down the instance HK and the instance G for your oracle and do this division here. And the target parameter would be the size of the pattern that you call with, but the size of the pattern is just exponential in K. So the size of the pattern is bounded by a function in k, and this is an FPT reduction from counting k cliques to the problem, so it's sharp W1 hard. So it seems here that we have an assumption that allows us to at least get rid of this one pathological case that I mentioned earlier. So, okay, let's just collect this. So this particular Sharpie intermediate class that I mentioned earlier, we can handle it in the parameterized setting. We also get useful statements when n is much larger than k, because this is what parameterized complexity is all about. But we have a new problem, and this new problem is just we actually don't answer the initial question that we wanted to answer. We just look at a different problem, and we'll use different assumptions, and we'll probably get a different answer. But for weird, or maybe reasons that can be considered weird, actually, this doesn't apply. So actually, if we just ask ourselves this question, we end up with an answer for the polynomial time solvability of this problem. And to elaborate on that, I would finally have to state this dichotomy that I've been teasing you with for the entire introduction now. So finally, we can actually do this thing that I mentioned in the beginning. We can try to state and prove some dichotomies. So the problem that we're looking at is, just as a reminder, counting subgraphs from a class C. What we have to do for this whole stuff to work is we have to assume from now on that the classes we're talking about are all recursively enumerable. So that's an assumption that we have to do for the parameterized reductions to work. But let's just say that this is probably an acceptable condition on a class. And then the dichotomy criterion that we end up with for this situation is we get a dichotomy along the maximum matching size in the class C. So the maximum matching size in a class is just the size of the maximum matching that you can fit into any graph of your class C. So there are essentially two situations that can apply. You can be bounded. I mean, this number can be bounded by a constant that depends only on C, or it's unbounded if you can find all matchings in there. So if this number is bounded by some constant, then it turns out that there is actually a polynomial time algorithm for counting subgraphs from the class C. So examples for such classes would be the class of stars, because you can find only one matchings in stars. Generally, all classes that have bounded vertex cover number. Actually, the classes that have maximum matching number bounded by a constant and the classes that have vertex cover number by a constant are the same classes, because these two parameters are just bounded away from each other by 2. And essentially, this algorithm just works by generalizing this idea that gave the algorithm for stars. But rather than just mapping this one center vertex into your graph, you now have to map the entire vertex cover into your graph and do some dynamic programming once this mapping is fixed. But since the vertex covers have just constant size, you can just brute force all the mappings for the vertex cover. And then you can see that you end up with a polynomial time algorithm. On the other hand, if you don't have a bound on this maximum matching number, then the problem is sharp W1 hard. So this situation applies in a minimal case if the class is that of matchings, but it applies also for paths and cycles, because in both of these graph classes you can find arbitrarily large matchings. And generally it applies whenever you can find graphs in which you can fit large matchings. And again, let me just stress that in this dichotomy, we actually get a classification when counting subgraphs is polynomial time solvable. And the assumptions that we have to make here are that FPT is not equal to sharp W1. So we assume something in parameterized complexity and we get something in classical complexity. And again, there are sharp intermediate cases for this problem.
So if the matching size is super constant but significantly smaller than K or kappa or whatever is the right, is there some intermediate complexity that appearing in the constant? So instead of n to the O1, it would be something like n to the size of the matching?
Well, it's always n to the vertex cover. Oh, okay, it's n to the 2 to the size of the vertex cover, essentially. So let's say if you have log size vertex covers, then you could still get quasi-polynomial time.
Okay.
Yeah, that would still work. But then things become a bit unclean because now you really have to incorporate the actual size of your vertex cover into it. Okay. So that's our dichotomy for counting subgraphs. There are similar dichotomies, so let me just write this one as in this particular format here. So if we want to count subgraphs, then bounded matchings makes it easy, and otherwise it's hard. If you want to count induced subgraphs, the situation is much worse for tractability. So whenever your class is finite, then you can trivially do this in polynomial time. On the other hand, whenever your class is infinite, then it's sharp W1 hard. So here, for instance, stars were easy, but here they are not. I mean, they have bounded matchings, but there is an infinite number of stars. So stars are hard. Things become easier if you go to homomorphisms. So if you want to count homomorphisms from a class C into host graphs, then by a result of Dalmau and Johnson, this is polynomial time solvable if the class has bounded tree width. Otherwise, it's sharp W1 hard. And I will describe later what tree width means. And we get the same situation for counting colorful subgraphs, where your subgraphs now additionally have colors on them, and you want to respect the coloring. I will also elaborate on that later. But again, here the criterion is bounded tree width. And these are weaker conditions on a graph class than having bounded matchings. Because, for instance, tree width is a measure of tree likeness, and in particular forests have tree width 1, but matchings are forest. So matchings are hard here, but they're not hard here. And in all of these cases, we have intermediate cases. So in all of these cases, you can kind of consider all of these cases as some kind of success story for FPT versus sharp W1.
What is the reference? Is CTWOA?
This is Chen, Thurley, and Weyer. EGR Chen. There are a lot of Chens. Okay, so these are dichotomies that are obtainable. Now let's get back to this subgraph counting problem. In the remainder of the talk, I'll try to sketch a proof for this. And the basic outline for the proof is that we first look at the tree width of our class. If the tree width of that class is unbounded, then we can get a reduction from counting grids. That makes the problem sharp W1 hard. And that's a relatively often used technique so far. Okay, I'll elaborate on that later. So that solves the problem if the tree width of C is unbounded. If the tree width is bounded, then the next thing we do is we look at the matching number. If this matching number is bounded by a constant, then we get these polynomial time algorithms that I mentioned before. If the number is unbounded, then we get a sharp W1 hardness result by reducing from counting K matchings. So this is essentially the case distinction that we have to make to get the dichotomy. And I want to talk first about this unbounded tree width case where we get a reduction from counting grids. So to get the hardness result for counting subgraphs, we actually first look at the problem of counting colorful subgraphs, because it turns out that working in this setting is much easier, and we can work efficiently in this setting if we have unbounded tree width. So the situation for counting colorful subgraphs is that we again have patterns. We have a pattern H and a host graph G, but now both of these graphs have colorings on them, so the vertices are colored with K colors. And the graph H has additionally this restriction that its coloring must be bijective. So the graph is colorful. And colorings in this setting are not necessarily proper. So what we now want to look at is the number of color-preserving H copies in G. And we denote this by this number col sub. So color-preserving H copy in G is just a subgraph of G that is isomorphic to H by an isomorphism that maps only vertices from one color to vertices of that same color. And then you can again define a problem for general classes. So given a class of graph C, the problem would be on input a colorful graph H from the class C and the colored graph G. Parameter size the pattern, count these number of colorful subgraphs of H and G. And this is kind of useful because you can see that this colorful subgraph problem can always be reduced to the uncolored subgraph problem by an application of the inclusion-exclusion principle. So essentially you get an FPT reduction, and this reduction really needs FPT time. We can't get it in the polynomial time setting. You get an FPT reduction from the colorful problem to the uncolored problem. And this is extremely useful because, okay, so at this point I have to define what tree width actually means, but I won't do it. I will instead define what it means to have unbounded tree width. So a class is unbounded tree width if, and this is a deep result in graph structure theory, class C has unbounded tree width if for every n there is a graph H in your class such that the n by n grid is a minor of H. So the grid is just this square grid here, and being a minor just means that you can get the grid from H by doing vertex and edge deletions and edge contractions. Let's abbreviate this bulky statement by grids are minor contained in C. And then we just claim that this uncolored subgraph counting problem is sharp W1 hard whenever C has unbounded tree width. And to do that, we show that the colorful subgraph problem on grids is sharp W1 hard. This is not too hard. You can use a reduction that is actually a polynomial time reduction and preserves the parameter. Then the next thing you do is you show that whenever you have a class C that contains grids as minors, then counting colorful subgraphs on C is also sharp W1 hard because there is an FPT reduction between these two problems. This holds generally whenever a class is minor contained in another class. So this problem is, so to say, minor monotone, complexity-wise. And then in this last step, we just reduce the colorful problem to the uncolored problem. And it's really at this step here that we need this excluded grid theorem, because this tells us exactly that, C has unbounded tree width. Okay, if C has unbounded tree width, then we can find these arbitrarily large grids in C, and this is exactly what enables this reduction. So this is kind of nice because this is one of these situations where we can really use this power of parameterized reductions to invoke some heavy graph theoretic machinery. Because for a long time, actually, to get an n times n grid, you would need to get a graph of exponential size. Actually, this was brought down to polynomial in the tree width by now, but this doesn't matter, really. The graph class C could still be arbitrarily sparse, but it's recursively numerable. Okay. So anyway, this shows that counting subgraphs is hard if C has unbounded tree width. The next step is we have bounded tree width, and we have unbounded matching number. So then the reduction is from counting K matchings. And I'll first show that counting K matchings is actually hard. And this is a slide that I've been reusing for the past 3 years now. It's showing a person who tried to count 3 matchings and collapsed over the task because it's hard, which is what I'm going to show now. So I want to end up from some sharp W1 hard problem at this problem of counting K matchings. And this initial problem that we're starting with is counting colorful subgraphs where the pattern has maximum degree 3. So by this classification that I gave on these previous slides, this problem is sharp W1 hard. Because if you look, for instance, at a hexagonal lattice, then you can see that you can draw a grid on there. So the tree width of these lattices is unbounded, and the problem is sharp W1 hard. Then we reduce this colorful subgraph counting problem to counting colored matchings, which are not necessarily colorful. Actually, colorful matchings are easy. And from these colored matchings, we go to uncolored matchings, again by this inclusion-exclusion principle, which we also use to go from the colorful subgraph problem to the uncolored one, and which I didn't mention. But yeah, it's the same technique. So to actually get this hardness result for colored matchings, this is the initial instance that we reduce from. So we're given these colored graphs H and G, and we're interested in the number of H copies in G. So previously I wrote col sub for this number. Now I just write sub to abbreviate a bit. What we're going to do now is that we pick a vertex, let's say this vertex V here, and we explode it. This way we end up with a graph H prime. And exploding a vertex just means that so this vertex V had two edges incident with it. We replace V by two new vertices, which are on the same color. And we redistribute the edges that were incident with V to these new vertices, such that each vertex gets one edge. Then we end up with a new pattern H prime. And we show that if you can count H prime copies in graphs, then you can solve this original problem by constructing two instances, G1 and G2, such that you want to count H prime in G1 and G2 each. This gives you two numbers, and some linear combination of that will give you this original number that you're interested in. So let me sketch briefly how these instances are created. So if H prime is obtained by exploding this yellow vertex, then Gi for I equals 1 and 2 is a graph that you get by just adding I minus 1 clones for each yellow vertex. And you can see that if you count H prime in G1, then you actually just count H prime in G, because G1 is just G. We didn't do anything. But if you count H prime in G2, then there are essentially two things that can happen for an H prime copy. So either the two yellow vertices that you have from this explosion go into the same block. Then if you contract that block, or if you contract all blocks, you end up with a copy of H and G. And each copy of H and G can be extended in two ways to such an H prime copy, because you can take this way or the other way, where the blue vertex would map here and this one would map here. Or the other thing that can happen is that these two yellow vertices hit two different blocks, and then you end up with a copy of H prime in G, and each copy of H prime in G can be extended in four ways to a copy of H prime in G2, because at each block you have two choices, and these choices are independent. Okay, but this is the number that we want to have, and these are the numbers that we can get by oracle calls. So we have a linear system of equations that is kind of obviously invertible. So in other words, if we get these numbers, then we can recover this number. Okay, and the very same approach also works if you explode a vertex of degree 3, then you just end up with 3 new instances. So, yeah. Okay, these are the basic operations that we have. And now we want to combine this to end up in a reduction from counting colorful subgraphs to counting colored K matchings. So again, the initial problem is we have this pattern H, which is colorful. It has K vertices, L edges, and its degree is bounded by 3. We want to count that pattern appearing in a graph G. So the first thing we do is we explode some, let's say this yellow vertex. We get a copy of H prime, we get a new pattern graph H prime, and we get two new host graphs G1 and G2. And we count H prime copies in G1, and then H prime copies in G2. But to count H prime copies in G1, we actually construct a new graph, H prime prime, where we explode this green vertex, and we get 3 new instances, such that this number can be recovered from these 3 numbers. We do the same for G2. And you can see that if you do this whole thing K times, then you have exploded all vertices. And you end up with a colored matching, because now every vertex has degree 1. This colored matching has L edges. And altogether, you have at most 3 to the K graphs. So this is an FPT reduction, because it runs in time at most 3 to the K. And the target parameter, if you started with a graph on K vertices, you now get a matching on L edges, but L is O of K. So you have bounded the parameter by this as well. So that's a parameterized reduction from counting colorful subgraphs to counting colored matchings. This second reduction, again, as I mentioned before, is is an application of simple techniques like inclusion, exclusion. Okay, so this concludes the hardness proof for K matchings. So we have sharp W1 hardness of K matchings now. What we now need is a reduction from counting K matchings to this general subgraph problem. And what we're using for this is some Ramsey theoretic argument, which shows that whenever you have a graph class that has a bounded tree width but unbounded matchings, then you can actually see that this class has unbounded induced matchings. This is not particularly hard to see, but the thing is that this argument allows us now to classify hereditary classes quite easily. So we get the dichotomy for hereditary classes. These are classes that are closed under induced subgraphs. And why is that? Well, just if you look at the tree width, and that's unbounded, then we have the sharp W1 hardness result, which I mentioned before by this grid type reduction. If the tree width is bounded and the matching number is bounded, we have polynomial time solvability. If the tree width is now if the matching number is now unbounded, then this thing here tells us that we have unbounded induced matchings in the class C. But since C is hereditary, if you have induced matching of size K, you can just delete everything that is not part of that induced matching, and you just get this induced matching, which is just contained in C. So you don't actually have to do any reduction. Your matchings are just contained in the class. So you get sharp W1 hardness here as well. And if you want to do this for non-hereditary classes, things become much more complicated. And I would be happy to talk about this offline, but since I have only, I think, 5 minutes left, I cannot include this in the talk. So let me conclude the talk by showing some other models for counting subgraphs that I also want to mention. So one of these models that is quite interesting also is counting modulo 2. So this is quite recent work that I'm doing with Holger Dell and Tore Husfeld. So in this counting modulo 2 business, we're looking at the parity version of the subgraph counting problem. So here you're given graph H from a class, and again, your host graph G, you parameterize again by the size of the pattern. But now you're just interested in a number of subgraphs modulo 2. So one thing that is known is, okay, permanence modulo 2 can be solved in polynomial time. So you can count perfect matchings in bipartite graphs in polynomial time, just because permanents are determinants modulo 2. And actually you can generalize this. So, okay, permanence modulo 2 in polynomial time means that perfect matchings in bipartite graphs are easy. But actually, matchings of arbitrary size in general graphs are easy, modulo 2. You first have to do interpolation on the matching polynomial, and then to get non-bipartite graphs, you just have to do some simple construction by just doubling all edges and observing that only perfect matchings survive this. So in other words, the subgraph counting problem is polynomial time solvable if C is a class that contains only matchings, like here. But actually, we can generalize this to show that if you have a constant C such that every graph in C is C matching splittable, then the subgraph counting problem modulo 2 is still polynomial time. And a graph is C matching splittable if you have some defect set of size C. C is a constant, such that if you remove this set, you end up with a matching. In this setting, a matching is a graph that has degree at most 1. So in other words, if you just take a matching, and we know that matchings are easy, then adding a constant size set won't make it harder. And on the other hand, we can show that if this is not the case and C is additionally hereditary, then the problem is parity P hard. But unfortunately, we cannot yet get rid of this hereditary restriction, and we also don't have the hardness proof under parity W1 so far. So this is kind of recent work in progress. And one interesting thing to note about this is that the very same dichotomy criterion applies for the decision version of deciding whether a graph contains a subgraph from a class. So, I mean, assuming that C is a hereditary class. So Bart Janssen and Daniel Marx have shown that exactly this this criterion here classifies the easy and hard cases for deciding the existence of a subgraph. And in a certain way, this stuff that we're doing here kind of indicates that, well, counting modulo 2 doesn't seem to be harder, at least in the subgraph counting model, if we're talking about polynomial time solvability on hereditary classes, than deciding. So here we cannot identify new hard cases. Okay. And then the other model that I also want to briefly talk about is one that was introduced by Mark Jerram and Kitty Meeks. And I'm drastically oversimplifying their model to make it kind of presentable for these slides. They have a much more general model. But let's just say that their model is counting-induced subgraphs phi for a fixed property phi. So phi is just a function that maps graphs to 0 and 1, or 1. And the input for this problem is a graph G and a number K. You parameterized by K. And the output that you're interested in is the number of sets X that have size K. And if you take the graph induced by this set X, then this would be a model for the property. So what they showed, for instance, is that H is the property of being, if phi is the property of being connected, then you end up with sharp W1 hardness. The same applies if H has an even number of edges or an odd number of edges, then you also get sharp W1 hardness. But somewhat more generally, they showed that whenever you have a graph class, so whenever you have a property phi whose edge density is subquadratic, then you also get sharp W1 hardness. And the edge density of a property is defined as follows. So this density of phi for a number k is the number of different edge numbers that you can get by looking at all k vertex graphs that satisfy your property. So for instance, if you look at all graphs, then this edge density would be, well, it would not be subquadratic. But if you, for instance, look at the planar graphs, then you have a linear upper bound on the edge densities that occur. And in other words, okay, whenever this edge density is not quadratic, then they can use some Ramsey theoretic argument to show that you can identify large cliques or large independent sets, and then they reduce from that to get hardness for this thing. Okay, this concludes my talk. Thanks for your attention.
Questions? Can you give a hint as to the connection between this and classical Vertex? It's something you were deducing classical results from FPT results? That seemed to be what you were saying earlier in your...
Yeah.
Or is it not possible?
So the thing is just that we get a dichotomy where actually, so we get an FPT versus sharp W1 hard dichotomy, but the FPT cases just coincidentally turn out to be polynomial time cases. And that's it. That's literally it. I mean, this just establishes that if FPT is not equal to sharp W1, then these sharp W1 hard cases, they cannot be polynomial time solvable.
Oh, I see.
That's all that happens. It's a magical coincidence that FPT-ness coincides with polynomial time solvability, but this applies in many settings. So not just for counting subgraphs, but also for counting homomorphisms or colorful subgraphs or induced subgraphs.
Is it also for deciding the existence of a homomorphism, not just counting it?
Yeah, deciding also works, but then it's the tree width of the course that you have to look at. Yeah, and for finding subgraphs, we don't really know what's going on. So we know that the problem is FPT if you have bounded tree width. We know that it's polynomial time solvable if it's matching splittable, but we have, I think, no lower bound at all. So in particular, we don't know whether the unbounded tree width cases are W1 hard. So we know that cliques are W1 hard, and actually I think it took the field until last year, I think, to show that bicliques are W1 hard. And this was a major breakthrough. So we are quite far from classifying the unbounded tree width cases. Maybe there are things that are somewhere in this kind of non-clear boundary that I try to draw that actually show that maybe this is not the right criterion. I don't know.
So in the model where you're counting induced subgraphs with property phi, so do you think that the answer is if phi is determined by a set of edges which have bounded vertex cover, there should be. The rest is.
It should be.
Yeah, it's polynomial.
Right.
And the rest is.
To be honest, I don't really know I don't have too much of an intuition about the property setting.
Right. Yeah. Given your result,
it would be reasonable to believe that, I guess, but I have no strong reasons to believe it, to be honest, other than it would give a nice, clean dichotomy.
Thank you.